Yeah, so your question is about plotting x1 versus t. So to do that, and it's just a sketch, it doesn't have to be exact, but to do that you start with the phase portrait which graphs x1 versus x2, or in the language of this picture here, x versus y. It doesn't matter your symbol choices. But anyway, so given a system of x and y, both of which depend on time, let's think about how we could sketch a solution trajectory of x versus time. So let's say that we start, let's say right here, this is 2.5, 2.5. So let's say we start right there, so time starts there. Well, since you're at the point 2.5, 2.5, x is 2.5 at time 0. So if you're going to start a plot of x versus time, you would start with a little tick mark or a little dot at 2.5. That's where time starts. And then you watch the flow. So you're going to flow like this, it looks like. Flow, 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 until you get to about, like 0.5, 0.5 or something, and then you turn and do this and flow towards 1. So over time, what's happening? X decreases from 2.5 all the way down to about a half. And then at about a half, x turns around and increases to 1, and then camps out at 1 forever. So it looks like 1, 0 is an equilibrium of the system, which means once you reach it, you don't move away from it. So if you're going to plot a graph of x, you're going to start at 2.5. You're going to fall over time. And again, this horizontal axis here is time. It's not clear how long this is taking. Okay, so it's just a sketch. But over time, you're going to fall from 2.5 to about a half. So like right about here. All right, so plotting this flow here. X is falling from 2.5 to about a half. Right, because there's a half right here, right? You're just tracking x, what x is doing. So fall, 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 x is about a half right here, and then we turn around and go right to 1. So in your graph here, you're going to go 2.5, down to about a half, oh, but then we turn around and we go up to 1, and you're actually going to asymptotically approach 1. You actually won't reach 1, you're just, as time moves on, you're going to get arbitrarily close to 1. So in this graph here, there's going to be a horizontal axis, or a horizontal asymptote at 1. So I can't make this thing sketch it, but you can just watch the mouse, right? It goes from 2.5 or so down over time to about a half or so, and then it climbs and it will level off at about 1. So that's how you can take a phase portrait and sketch what happens to x or y over time. So if we do the same thing with y, so we start at this point here and track what y is doing. Y also falls, so you just keep going, going, going. Y is falling also until about, like right here, y is maybe at like 0.75. And then you fall, fall, fall like this, right? So y, unlike x, y just falls from 2.5 down to 0. Right? So if you're going to graph y starts at 2.5, and over time just kind of like, it'll fall kind of like this. 2.5, down, 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 and then it will asymptotically approach 0. So you can see right here, x's actually turn around, don't they? Right? X's fall to a half and then increase to 1. But y's over time just fall. There's no rise in the y. So I hope that has cleared it up. That's how you, so essentially to answer your question, you have to start with a phase portrait. Since we can't actually solve these systems, okay, we are not actually solving this. To solve it means getting an equation that looks like, x equals a half e to the t plus sine t or whatever. We're not actually doing that because we don't have the tools to do it. This is a qualitative way rather than an exact analytical way of analyzing these systems. So it's all just giving you a broad idea of what's happening. Nothing is exact here. So anyway, if that doesn't clear it up, just let me know.